Today we're going to be talking about some special triangles. We're going to talk about the isosceles and the equilateral triangles. We talked a little bit about them in our previous lessons, but we're going to build on that information. We know that an isosceles triangle, by definition, has two congruent sides. Those congruent sides, they are going to call the legs. And the third side, the non-congruent side, they're going to refer to as the base. Therefore, we are also going to be talking about base angles. And the third angle they're going to call the vertex angle. A lot of times they'll talk about the vertex angle kind of as, or we think about it as being the angle at the top. Although that doesn't always have to be true because our triangle can be rotated. So if we take a look at our isosceles triangle theorem, it says that if two sides of a triangle are congruent, then the angles opposite those sides are also congruent. Well, those angles opposite those sides, they're really referring to the base angles being congruent. So as I look at my picture and I have my isosceles triangle here, my two base angles would be angle A and angle B. So angle A would have to be congruent to angle B because I know that my side AC and my side BC are congruent. The converse of that is also true. The converse says that if two angles of a triangle are congruent, then the legs opposite those angles are congruent. So as you can see in my triangle, if I only know that angle A is congruent to angle B, well, I therefore can conclude that side CA would have to be congruent to side CB. And finally, the bisector of the vertex angle of an isosceles triangle is the perpendicular bisector of the base. So as we look here, I can see that my vertex angle is being bisected. Therefore, this segment is also going to be the perpendicular bisector of the base, meaning it's going to meet it at 90 degrees and it's going to bisect. Therefore, we would know point D is a midpoint. They're going to ask us to do a little bit of solving today. In example A, I can see that I do have an isosceles triangle. My two sides are the same. Therefore, I know that my base angles are also going to be congruent. This angle congruent to this angle. Now they're asking me to find angle H, and I certainly could just subtract from 180 and divide by 2. I could also think about setting that up algebraically by knowing that my angles being congruent plus my vertex angle would have to add to 180 degrees. So that's another way that we could look at this. If we did a little bit of simplifying, we'd have 2x plus 48 equal to 180, and we would go ahead and we would solve for x. Now I find out that x is 66 degrees, and therefore I know that angle H would equal 66 degrees. In number 2, I again see I have an isosceles triangle, and therefore my base angles will be congruent. Well, here, my base angles are going to be N and P. And if they are congruent, I then know for that 6y would have to equal 8y minus 16. And we would go ahead and solve. If I decided to subtract my 6y, which some people may do, I have to remember that I'm going to put that equal to 0. And then I'm going to add my 16 over. Looks like I'm going to find that y is equal to 8, but I need to remember that they're actually asking me for angle n. So I need to take that and I need to plug that in. 6 times 8, and we would find out that angle n is 48 degrees. Flipping our note sheet over, on the back side we're going to be talking about our equilateral triangle, and we have a couple corollaries at the top. It says that if a triangle is equilateral, then my triangle is equiangular. Here I can see that all sides marked congruent, meaning also that my triangle is going to be equiangular. We had previously discussed the fact that our equiangular triangle has to have angle measures of 60 degrees. Well, the converse of that corollary is also true. So if I know my triangle is equiangular, I can say that it is also equilateral. So if I simply have a triangle with 3 congruent angles marked, or 60-degree angles, I know that my sides would all have to be congruent. And so really, you can think of that as a biconditional. A triangle is equilateral if and only if it is equiangular, meaning it is true both ways. So as I look down at example B, and we're going to do some solving, I see that this triangle is marked equilateral, but I'm actually looking to solve for x, which has to do with angle L. But because it is equilateral, I know that angle L must be a 60-degree angle. And so we're simply going to take 2x plus 32 and set it equal to 60 degrees. And we find out that x would be 14 degrees. In example number 2, as I look, they have my triangle marked equiangular. But they're actually asking me to take a look at the side lengths. These are asking or showing me side values for t minus 8 and 2t plus 1. But because I know it's equiangular, I also know it's equilateral. And so we know that 2t plus 1 would have to be equal to 4t minus 8. And we can go ahead and solve from there. I'm going to add 8. Subtract 2t. Now in this case, t does come out as a decimal, but that's okay. It's 4.5. That's a pretty nice decimal. I'm not too alarmed by that. It's only when I get a decimal of, 4.51627 that I might be a little bit concerned. So that concludes our discussion on isosceles and equilateral triangles. If you have more questions on those, please see me.